right, good morning, everyone. Welcome to this week's CIS seminar. It's a great pleasure to introduce today's speaker, Professor Shantenu Jha. He's Professor of Electrical Engineering and Computer Engineering at Rutgers University, and he's also the head of Computational Sciences at the Princeton Plasma Physics Lab. Before that, he was also the chair of the Department of Computational Data Science, I think, at Brookhaven National Laboratory. So he has a broad experience in that. He got his undergraduate degree from the Indian Institute of Technology in Delhi, and then moved to the US to pursue a master's degree and a PhD degree at Rutgers University, and then spent, I don't know how many postdocs, but I know one of them was at UCL. I also spent some time, we didn't have any overlap, but some people technically say that we're kind of academic siblings. Professor Shantenu is very well known for his work in HPC. He is one of the developers of the Radical cyber suite of tools, which is incredibly useful for domain scientists to run applications on the largest supercomputers that we can get access to. And he has since moved on to develop combined HPC and AI workflows, which he will talk about more today. And I'm really excited to learn more about that. So thank you very much for joining us today, and I look forward to your talk.
Thank you. Thank you for the invitation. Thanks for the opportunity. And yes, we are academic siblings, but Ulf is the younger, the better sibling, as opposed to the grumpy, misguided sibling. So with that, thank you. It's a pleasure to be here. Thanks to be great to be back amongst many friends. So, hey.
Sorry, went to the wrong place.
Better late than never. Great. So the goal of today's seminar is really educational. I don't think you're going to learn very deep details today. I'm going to go broad on purpose, because I know when you're talking to a large number of graduate students at a time like this, different backgrounds, there's a lot of concurrent interests. And so I'm going to try to speak to the many strands of interest. Two things. A, feel free to stop me, questions, clarifications at any point. Don't wait till the end. So just want to give you that license. The second thing is, if there's one message I want you to take away, for those of you who want to go back to checking emails, or now that you've signed in, have gotten your credits, need to leave. I've been on that side of the fence. Don't worry. We know the tricks, right? So if there's one message I want to impart at the beginning of the lecture, it's the following. We're living in interesting times, and high-performance computing has played a critical role in so many things we've done. Vinit's worked on a project called Impeccable. Impeccable was responsible for coming up with one of the first drug candidates during COVID, right? Just to give you one example of societal impact of high-performance computing. The point is, high-performance computing is going through a fundamental change for a set of reasons I'll get into: technology, economics, and obviously methodological. And it's a super exciting time to reimagine how we do science in the years ahead with this major change in high-performance computing. And if there's nothing else that you learn, A, we're at this very important inflection point. B, we're starting to see some amazing science happen that we would not have imagined could happen in, let's say, such a short time, thanks to the convergence of high-performance computing and AI. All of you know about the amazing things that AI has done, but the real impact is not in the chat GPTs. The real impact, I would like to argue, is going to be in how science is done and discoveries are made. Very early on, but hopefully I'll give you small glimpses of the success stories, and hopefully many more to come. Okay, so Ulf pointed out my affiliations. I'm going to begin by abusing my affiliation with the Physics Plasma Lab at Princeton, and try to take you through for the first 5-7 minutes, just walk you through something which is a grand challenge, fusion, sustained fusion, zero carbon, essentially infinite energy. And I'm going to walk you through fusion, not because I know anything about fusion, as I was telling Ulf and his team. I knew zero, almost zero, and the good thing is I now know twice as much as almost zero in 6 months' time, right? So it's not because I'm a fusion expert, but I want to lay fusion as an example as a field that has benefited from high performance computing, but as a exhibit A, that without some of the advances I'm going to talk to you about, there will be no fusion as we hope it will be. Okay, so what is fusion? For those of you who may not have had a refresher for the fundamentals, it's the opposite of fission. Basically, instead of really kind of high energy, having something fuse, dissociate, you're trying to bring two particles together, subatomic particles together, and in the process, have an immense amount of energy that is left, right? That is released. And you obviously know this is essentially the difference in the mass between the starting point and the end point. That mass gets converted into energy, right? As simple as that. And that's a very large amount of energy. Okay. And you probably all know this, that fusion is what powers the stars, the sun in particular. The stars have an advantage, as you can see. The core is 15 million Kelvin, a small but non-trivial amount, right? And that pressure, that energy makes this reaction, makes this process fairly easy to carry out at 15 million. But we're trying to build fusion devices right here on Earth in lab. We don't have the same scale and forces of gravity in the lab, right, to state the obvious. So what do? We build devices, reactors. Some of them are called tokamaks, stellarators, different kinds. But the challenge is, because we don't have that size and scale of the sun and the gravitational and various pressures, we unfortunately have to go to 10x higher. So at a minimum, 150 million kelvins to provide the right energies in order for that fusion reaction to happen. Okay, sounds very simple. We call this a star in a jar, a sun in a box, right? This is not real, this is schematic, but that's really what we're trying to reproduce, right? If you will, this is the size of a couple of human beings, 12 feet, depending upon the specifics of the device, right? But order 10 meters, just as to set the scale, right? At Princeton lab, we use magnets as a way of confining this plasma, this charged high energy set of particles. But there are other ways of confinement. Some of you might know the amazing story of inertial confinement fusion at Lawrence Livermore a couple of years ago, where they used lasers to try to create the fusion conditions. So there are many ways in which the fusion conditions for fusion can happen. But the one we're most comfortable with is exceptionally strong magnetic fields, and that's called magnetic confinement. Right? One major challenge is, what's the right type of device to create that will have the right properties of confinement and control? Confinement is just one aspect. You need to be able to control it. You need to be able to respond to it, because sometimes disruptions happen. I'll tell you in a minute. And so there are many different possible geometries, structures, confinement device topologies. And here you see a small scattering of the 3 or 4 most common ones. In a year's time, we'll have something like this, which is a spherical tokamak operating right in the lab on campus. But right now, the largest device of the kind of fusion device that is planned. Who knows which is the largest device that is planned? ITER, International Thermonuclear Experimental Reactor, a $50 billion effort. And this, just for scale, a human would be somewhere here. So you start seeing the size. This is being built in the south of France. Okay, but I think the point I want you to appreciate is fusion as a source of energy is arguably truly important for economic and technical reasons and power. But as you start seeing, also for geopolitical reasons. But it is essentially a limitless clean source of energy, essentially zero carbon. And the impact of that can't be overstated, sorry. However, building a controlled reactor that can give us fusion on tap, on the grid, is anything but an easy activity. And I hopefully in the schematics that I've shown you, you appreciate why. You've got exceptionally large temperatures, pressures, immensely strong magnetic fields, and you've got charged particles moving in this field at close to relativistic speeds. So you've got a confinement problem, you've got to maintain the plasma at those temperatures, 150 million. You've got to build materials that can withstand 150 million Kelvin, not something you can go to Walmart and buy, right? And then obviously you need the controls and the engineering systems to be able to not just confine, but have it respond, because you're going to send in shocks, try to create the plasma conditions, so on and so forth. So I hope I've, without getting into details, at a very hand-wavy level, convinced you that this is a societally important problem, but a technical grand challenge. And there are many jokes about fusion. One of the favorite jokes is fusion's 20 years away. It always has been and always will be. Right? You've heard that joke in different contexts. There is an unfortunate element of truth to that. And again, many reasons, but one element is, unlike, let's say, if you're trying to understand the blood flow in a artery or in the human system, not that that's an easy problem, but it's a controlled, it's a bounded problem. This is essentially, by many accounts, an unbounded problem, because not only is it multi-scale, multi-physics, it has some of the highest magnetic intensities that you can think about. It not only has regular fluid dynamic style turbulence, it has whole different causes of plasma turbulence, many nonlinear interactions, and obviously you need to control this, and the list could go on and on and on. The upshot is, and this is the punchline of this part of the talk, is fusion's a grand challenge problem, and one of the many reasons why it's essentially out of reach today, one, obviously, is that it is not amenable to high performance computing as we know it today, right? It's beyond the abilities. And I posit that if we are able to get to fusion, we will have to make fundamental paradigmatic changes in the way we use computing. Computing is and resourceful ways of rethinking, reimagining the computing problem is going to be necessary in order to get to the actual engineering challenge. Okay, and so I just try to give you some examples of what these challenges are. Things I've already alluded to, right? Each one of them needs to be solved in order to create a workable device, and each one of these is a grand challenge unto itself. Okay, so this is where I start getting controversial, especially coming from DOE space, where I say HPC is dead, long live HPC. What do I mean by that? Again, let's look at this slightly more technically here. I don't need to tell you that we know HPC is critical for understanding the plasma fusion reactor problem. This tells us the trends of the top supercomputer. I think this is the #1 supercomputer, which is El Capitan now, but could have been Frontier some days ago. And over a very large, over 3 to 4 decades. And what you see is a non-trivial, a very impressive growth that essentially is 1,000 times, 3 orders of magnitude every decade. And the fact that this has held for 4 decades Very interestingly, although this is for the world's fastest supercomputer, this trend has held for supercomputers, and this trend mirrors essentially a lot of what we all know as Moore's law, plus minus a few small factors in there. So super impressive and a testimony to the ingenuity of building these very large supercomputers. But here's the problem. I've just told you that traditional or HPC is not good enough for the kinds of problems we're talking about. I talked to you about plasma and fusion reactors. I'm sure if you were talking about other disciplines, understanding climate change, climate engineering, or others, you're going to come up with another number. But I do a back of the envelope calculation, and I say we are 10 orders of magnitude behind where we need to be. And my friends say, oh, you're 10 orders of magnitude off, right? So some people say we need 20 orders of magnitude more computing, right? 20 orders of magnitude does not come easy, but if you do a very optimistic calculation and ask how many decades will it take at a factor 3 orders of magnitude, well, let's just say some of you young minds will be ready to retire. Some of us will be 6 feet under, right? For sure. For sure. So that is under the very strong assumption that supercomputers will continue this exponential growth, right? That's a very strong assumption. We won't get into this in this talk, but that's economics, technical, and a whole bunch of other, not to mention fundamental limits that will require us to start thinking of quantum effects in our very hardware realization. That's if we're lucky, this will happen, right? But there's no guarantees, and if anything, there's high uncertainty that this will continue. And obviously, a phrase for the times of our politics, it's getting harder to make supercomputers great again, right? Okay, we'll leave it at that. HPC is dead. Long live HPC. I've hopefully convinced you that at least you see why I say that. So yeah, very easy to talk about problems. What's the solution? The solution is, as given in bold, I'm going to talk about workflows are the new HPC applications. I'm going to explain what that means in a while. Then I'm going to get down deep and dirty into a specific type of workflows called AI-coupled HPC workflows. And then in the last part, I'm going to be really fuzzy, really hand-wavy, and try to just show you some of the software systems that we're building, have built, and are building to support these AI-coupled HPC applications at the largest scales, largest supercomputers, right? So that's the, if you will, the template of what we're going to do over the next 35 minutes. Okay. So let's talk about the underlying technological trends. Just let's all remind ourselves why I make the remark, workflows are the new HPC applications. It's incumbent I try to put that on a firm footing. So some of you may have read this paper, which talks about there's plenty of room at the top, right? Which is a riff on Feynman's very famous "There's plenty of room at the bottom." It's talking about how design higher level software abstractions should be created to exploit the computational power of current and future generations of processors. Talk about a riff on the riff. I say, yes, there's plenty of room on the top, but there's even more room on the side, which basically is a way of saying when you put processors together, and importantly, you think about, obsessively think about moving beyond single task performance, you open up new vistas, right? And that's what I mean by, yes, get all the performance you can easily from a single node, single GPU, few GPUs, but start thinking of what you can do if you have many, many, many of them, right? So move beyond single task, single node performance. I'm conflating the two, but single task is few nodes, multiple nodes, right? So important, but think about what happens when you can go beyond a single task. And then also appreciate the fact, and hopefully those of you who are involved in the domain sciences will appreciate that scientific applications are increasingly more than single task. It's about a task that does something, but it's about orchestrating and assembling parts of an application into a whole. So some parts do traditional simulation, some parts might do some form of analysis, some part might do, let's say, inference. So you're trying to build all of this together. It is the natural expression where you stop doing a single scientific experiment as defined by a single simulation to thinking about campaigns. Let us do this for a certain amount of time until we get enough confidence, lower uncertainty. And once we reach a certain convergence, let's do this. You want this to be a single campaign which you program, and you want to submit that to the supercomputer as opposed to one task at a time or a few tasks at a time. Come back 24 hours later, analyze that, then based upon that, decide what you want to do, submit a job, wait for another 24 hours, right? So that's one thing. So there's thinking about the structure of scientific inquiry and discovery, thinking about plenty of room on the side, and thinking about the fact that over the past 20, 30 years, the impact that high performance computing has had is primarily because we have been successful at weak scaling, which is really a way of saying we solve bigger and bigger problems, not necessarily a certain problem for longer, right? So we've not really improved our ability to strong scale, take a fixed problem size and run that over longer and longer times, which is a way of saying, give me a big problem, but I want to solve that particular problem as quickly as possible, as soon as possible. Our ability there, if anything, is diminished today for a whole set of architectural, micro-architectural trends than it was some years ago. In some ways, it's gotten a bit harder to get longer timescales or run a problem and have it be solved sooner. And then just very quickly, a riff on the fact that you want to think about the computational campaign, the scientific discovery, the scientific inquiry. I just call out immediately that this kind of means you are now not just worried about the core kernel, your core MD simulation, for example, but you're worried about the whole campaign. You want to worry about the outer loop, the Bayesian optimization, the uncertainty quantification, so on, as first order considerations of your computational process. And important, we won't have time for this, but when you think about this in this way, you soon realize that yes, you need the parallelism at the lowest level, but the structure of the problem, this outer loop, is to try to extract parallelism and scalability at the highest level of the problem and not just at the lowest level of the problem, right? Okay. So very quickly again, there's a bit of a rehash, but just trying to put all of this together and more for context. We've talked about the fact that the peak capabilities of supercomputers unlikely to continue to grow. But an also important trend, and this is the real part of the slide, is that supercomputers will, in the future, I shouldn't call them supercomputers, say future leadership class machines, the top tier machines that the DOE labs and others manage, will become a hybrid of traditional computers and what we call cloud services or services for science, right? And so now there's a whole bunch of things you can say, should we be cloudifying the HPC or HPC-fying the cloud, so on and so forth. But the point is, what is the future architecture of the platforms on which traditional simulation, modeling, discovery, design will happen is a big question mark, right? It's not going to be the way it's been for the past 20 years. And again, a riff on this is to say that my colleagues in the DOE ecosystem are not talking about what's after exascale. They're talking about what's an exascale ecosystem. And this is just a simple schematic to show you that we're somewhere here, if I see this correctly, and OLCF6, the next generation, is being designed, thought of as an exascale ecosystem and not just a single exascale computer, right? And that really means a bunch of services for science applications. And let me just put it forward. Some of you may have heard of NAIR. This is coming out of the former White House, but with continuity in the current OSTP. NARE stands for National AI Research Resource. It is an aggregation of large, powerful, traditional supercomputers, but an aggregation of those supercomputers with cloud-like services for hosting AI systems, AI models, and future inferences. So we'll come back to NARE later, but just to tell you, NARE is not at the exascale. It's still powerful, but not at the largest scale. But you're starting to see the first steps towards that ecosystem. So some of you might know about Access. Ulf had a very nice way of saying, this is access many different systems for AI, right? And we'll talk about that, more about that later. Okay, so let me take 1 minute to talk about the scale of the problems I'm referring to before getting into AI coupled to HPC. So boring simulations, no AI here for a change. Just want to tell you that this is an example of a workflow as a new application, but a very simple vanilla workflow. And just to tell you, there's multiple levels of parallelism, multiple ensembles of a given simulation, multiple ensembles of another simulation, some level of coupling. You got to run them all together. And all I want you to appreciate is this is 8,000, this is 64,000 GPUs and approximately 400,000 CPUs, right? So this is on Frontier, the world's till very recently largest supercomputer, now the second largest supercomputer. And what I'm trying to show you is you've got a bunch of applications, bunch of tasks running on CPUs, bunch of tasks running on GPUs, and at any given instant of time, you could have 7,000 tasks, which is, if you do the number of nodes, this corresponds to, I think, 8,000 nodes. So you've got 8,000 tasks on approximately 8,000 nodes and CPUs. And this is just to say, this is some large campaign multi-stage. It's not just one single simulation, multi-stage as defined by different things, right? Doing different things, and you can see parallelism at different levels of dependency. So that's what a basic workflow is, but at the largest scale. So that's all I wanted to impress upon you. Obviously, this is all published. You can get this links to it. Okay, so that's what a workflow is. Many tasks running. Oops, sorry. And so now let me move on to AI coupled HPC as the specific type of workflows that I want to talk about. Workflows are the new applications. You saw an example of that. Now let's talk about a specific category of workflows, such as AI coupled. But what is AI coupled HPC? I briefly touched upon this. You are now talking about the concurrent execution of traditional simulation, lattice Boltzmann, molecular simulation, CFD simulations, choose your traditional simulation, and you've got AI happening together, running together. And importantly, the AI is influencing the simulation, and importantly, the simulation's influencing the AI, right? Coupled together. I.e., this is online coupled and not offline. It's not that you do your simulations today, generate the data, come back tomorrow, train the model, come back 3 days later, influence your simulations. No, this whole campaign is happening concurrently, adaptively. Okay, so just very quickly, this is the precursor of the Impeccable project, which is about, so Impeccable 2 is what Vineet and I are working on. Impeccable 1 was the first part. The only real difference is this did not have generative AI. This was just before the generative AI generation. And all I want to say here is, in a record amount of time, we created some of the largest computational campaigns ever done to go from a very large space of possible drug candidates through everything from binding, docking, to at this end was some super expensive quantum chemistry calculations, right? So a pipeline of, if you will, different granularities, different accuracies, and obviously different computational costs to try to come up with a particular drug candidate, which we then synthesize, so on and so forth. That's not what I want to get at. What I want to just get at is, this was a super large campaign, at scale, but super effective in getting a drug candidate in a very short amount of time, right? And sorry, this is what I wanted to point out. And this was a classic example of coupling AI to HPC at multiple levels. So at the very top stage is a problem which many of you know called docking, which is a very cheap and cheerful, relatively simple. But even though it's relatively simple, because you have to do docking for so many large number of possible candidates, you still want to speed this up, right? And you want to speed it up as fast as you can. So again, without getting into details, just to tell you, we sped up the docking by creating a surrogate for the docking, which basically gave us a few orders of magnitude higher throughput in the number in the candidates, drug candidates we could screen without loss of accuracy. That's the key. Speed without loss of accuracy. And what was this? This was nothing but a very state-of-the-art at that time, impressive convolutional neural network that allowed us to train on a large number of the docking data, and then subsequently just through a simple inference call, which is, let's say, somewhere between 1 to 100 microseconds, be able to determine whether this would be a candidate or not. Let's get to the interesting part. So you think of that funnel model. You have a large number of drug candidates you screened. Some of them are totally useless. Some of them are promising. Some of them are very promising. You want to only take the very promising ones to the next stage because the next stage is computationally more intensive, right? You want to do compute binding free energy, so on and so forth. What we do here now is when we're trying to compute the free energy of these when they bind, we want to speed up the dynamics. All we're doing here, again, take traditional simulations, have a convolutional or variational autoencoder that's monitoring the data coming out of the simulations and is steering the simulations in real time, right? And again, there's lots of details. All of this is published in IPDPS. You can get the details, but what I want to show you here in a nutshell is that by having AI steer the simulations, you're able to get to the final state of the binded protein 100 times faster at a minimum than if you were just doing regular simulations. So add a couple of orders of magnitude from the docking, add a couple of orders of magnitude from the ones that you've progressed to the dynamic stage, and you start seeing the amazing impact, the orders of magnitude and orders of magnitude improvement in the drug candidates that you're able to screen. Okay, so this is, just keep this in mind, this is the first example of what we call continual learning loop, where you're also starting to improve the model as we go. Now, we didn't do that here, so I just want to be very clear, but I want to call this out because we'll come back to this in a while. So here we had a fixed model. The model was essentially fixed throughout the entire campaign. We spent some time training it, but there's no reason why you can't be improving the model as you go because the simulations are generating data of relevance. Okay, so I hope you've gotten by now the gist of what I'm trying to say through this impeccable 1.0 example, that you can use AI coupled to HPC to improve by some orders of magnitude the limitations of traditional HPC. I call this scientific acceleration, and this is the real thing. Don't care about how many flops, but I do care about scientific acceleration. It's important to appreciate that it's not just AI overcoming the limitations of HPC, but at the same time, HPC being used to improve the AI, the continual loop. And I want to give you examples. But this is not something you can just log on to your favorite supercomputer and be able to do, right? That's many research challenges, many software engineering challenges, and obviously trying to bring the applications into this mode. So let's take a few minutes to do some terminology because it'll be important to focus on what I'm going to try to highlight as some of the important questions above. So AI can be coupled to HPC in many different ways. You can take a simulation and you can substitute a part of the simulation with an AI system, a surrogate. Classic example, you're trying to compute the force field in a molecular dynamics simulation, try to compute the forces on the atoms or the molecules in the molecular dynamics simulation. You, instead of computing the Hamiltonian every time, you just try to put a good AI system there, surrogate, which then converts this complex computation of the Hamiltonian energy into a nice inference call. And those of you who kind of looked under the hood, somewhere between 75 to 80% of the cost of a molecular dynamic simulation is in computing the forces at every stage. If you can replace that, wonderful. That's called AI in HPC, and you can find other examples in other domains. But basically, you're substituting a part or maybe the entire HPC with an AI system. AI out HPC is you don't touch the core computational kernel, but you put a AI system that's working along with the simulation, the vanilla simulation. And the best example of this is when I was talking about the protein binding folding, where you have a AI system that's steering the whole, if you will, computational campaign. That's AI out. So if nothing else, think of AI in, AI out. And then there's obviously AI about, but for the moment, just let me ignore that and say there's three in, out, and about. And importantly, they're not mutually exclusive. You're going to have something that has AI, have computational campaigns that have AI in, out, and about. And this is not kind of theoretical musings. I'm just trying to show you work that we've done. In this case, again, another COVID project where we have 4 or 5 different computational workflows working together, but with AI working with the traditional HPC workflows in different ways, sometimes AI in, sometimes AI out, but the point is the whole campaign. And this is, again, some very impressive work, which, as you can see, the multi-scale nature of it, you can see the multimodal nature of it. And this is just trying to put off the thing. So I'm now building up to, okay, very promising, very impactful, maybe. But how on earth do you actually get all of this working on your supercomputer of choice? Right? So that's what I'll spend the last 10 to 15 minutes, hopefully having motivated what is AI, what are AI-coupled HPC, some of the scientific impact, and most importantly, why you must start thinking this way. Okay, so I have a fondness for bad jokes, so if you will, the worst joke of all times. I am going to tell you a bit about the runtime systems we've developed. So why is running all of this AI-coupled HPC so difficult? Well, I hope you've appreciated, I could get into the details with specific examples, but even if you don't go into the specific examples, you'll have the slides, you can read the specific examples. But I hope you've appreciated at a high level that to run these workflows, these campaigns, you don't have just one type of task. You have traditional simulations, which could be MPI, OpenMP, and some variant thereof. You have a bunch of training tasks, you have a bunch of inference tasks, and if you look under the hood, you'll have them come in and out. Some are dormant, passive for a while, some become active, and the workload at time t will look nothing like time t plus delta, right? So the workload is changing, the set of tasks. Sometimes it might be all AI, sometimes it might be all simulations, and obviously some combination in between. So not only do you have different types of workloads that are all part of the same application, which you have to handle and manage, they have different temporal and physical sizes. I just point out here that in the Impeccable One example, we had tasks that had 7 orders of magnitude separation in their resource requirements, 3 orders of magnitude separation in their cost, right? In the temporal duration, sorry. So you get the idea. You've suddenly gone to an application paradigm where you don't have one or few homogeneous tasks. You have gazillions of heterogeneous in every possible dimension, spatial, temporal, throughput that you have to manage. And yes, start saying this is what I want to do is very good, but how do you actually manage their execution at scale? Remember, we're not doing this on the laptop, we're doing this at scale, 8,000 nodes, 400,000 cores, 64,000 GPUs. And again, just to repeat and belabor the point, the workload is changing, okay? okay? And this is just a nice schematic of what you have to do. And the point we're really looking at here now is you've got these applications, AI, HPC, you've got some coordinating engine, that's fine. That's not a trivial problem, but not the most interesting problem. But it's this, the hybrid workflow runtime system, right? And so just want to give you a very quick schematic of what we've developed. We call this Radical Tools, particular version of that, Rhapsody. And the idea is you have, imagine all of Frontier, 64,000 nodes, 64,000 GPUs and cores. And what you do is we put in the coordinator task. And this coordinator task is not a real workload, but what it does now is it takes over the resources after having gone through your Slurm or your PBS or what have you. It now creates a memory, it now creates a resource overlay, which then you, as in the application, has control over, i.e. you can then slice and dice the n,000 nodes and cores to suit your application's workload profile, right? So basically what I hope you see the challenge is you've taken what is really from a Slurm perspective, a single resource, 8,000 nodes. Now you've, after having gone through the Slurm resource manager, you are now managing every node, every core, and you're spatially, temporally going to manage this to fit the profile of your application, which is changing. So that's the real challenge. It's very easy to say it in one word, but that's where everything has to be done effectively. That's the impact of the runtime system. So this is just to say, you're now bootstrapping your resource agents all over. You're creating the right overlays for different types of tasks. You start populating the different types of tasks on the different nodes. And remember, you're doing this, your application, your middleware is managing all of this. And we can go through a sequence diagram of how this is all overlaid. But let's look at what the impact of this is. This is just trying to show you in what is less than 20 minutes, the number of tasks that you, now don't worry about whether this is a single core task, single node task, a machine learning task, or a simulation. Just at some level, they're tasks that are running. And you can see what this runtime system does, right? You can see within 3 to 4 minutes, essentially every node, every core is populated with a specific task, right? 400,000, right? You essentially order 1 million tasks or 100,000, depending upon your perspective, is now being managed. And obviously these are changing. So that's the role of the runtime system in these kinds of coupled applications. Now, take any 1 or 2 dimensions away and the problem becomes very, very easy. You take the heterogeneity away, the problem is much easier. You change the temporal uniform, make it all temporally uniform, very easy. You don't say a large number of different tasks, even if they're homogeneous. You say one large task. Slurm's been doing that for the better part of 50 years, not a problem. But as you relax them, I hope you start seeing why this runtime system is the star of the show. And this is the gory detail of the system view, right? So you see the software overlay on the node. Okay, I'd be happy to give a lot more details here, but I just want to get to the crux of what does this all mean in the last, 5-6 minutes. Okay, so now think of this scenario that I posited earlier, where you have NAIR, NSF's budding $400 million infrastructure. You've got the supercomputers, but you've got Meta's models, you've got Microsoft's model, all distributed across the country. I don't want to let go of the runtime system I've just shown you, we've painstakingly developed, that can run everything locally. We now want to do everything local on the supercomputer, but if need be, go out and do an inference on the model somewhere sitting in Seattle, right? Behind Microsoft's firewalls, right? So just to tell you, the next generation is extending the previous runtime system to include AI ML services, which could be local or remote, right? And this is just to try to tell you some of the basic performance. Don't take this too late. This is still very It's still very early on. Give me a second, there's something on my screen here. Still very early on. Thank you for a very polite way of saying I'll be unwelcome in 10 minutes. Thank you. Okay, so there you are. You got services that are running remotely distributed, but you don't want to forgo all the advantages of running at scale. This is just to show you some initial performance of running inference services as part of this workflow, but those inference services are not even yours. They could be Meta's, they could be OpenAI's, they could be anywhere, whilst running your campaign, your workflow as it is. And this is just to show you the performance of being able to run a large number, 640 different inference or training services as you want, whilst retaining your capability of doing everything else. As far as I know, there's nothing else in town in the game that allows you to do this right now. I'm sure there are some proprietary capabilities. I haven't talked about this, but this is all open source there for you to experiment with. And just to show you on both sides that the performance bottleneck is not so much in the service instantiation and bootstrapping, but ultimately it's in the duration of the services and obviously over the wire. So you've got to do obviously latency hiding. So a new set of performance challenges when you're doing remote and local AI services. But the important point is you are now doing your AI services from inside your application without having to worry about where your AI system might be and the power and beauty of that. Okay, so very quickly, last 3 to 4 minutes. I've told you about NAIR. This is just to show you the richness. There is no other system in the world which brings this many AI providers together, right? Just look at this. And yes, NVIDIA is one of them, so thank you, right? So there's all of these, and some of these provide hardware, some of these provide models, some of these provide API access to proprietary models, right? So imagine the richness and obviously multi-agency. Okay, what I want to tell you in the last couple of minutes is we're putting all of this together for what is arguably one of the most challenging problems, what is known as protein design. It's not the same as protein structure prediction, which is in itself a super important problem, for which, as many of you know, Demis and others got the Nobel Prize last year, the AlphaFold problem. This is the inverse problem. Give me a desired protein of a given function. How do I build that? So this is a project we're executing using the richness of the AI models that NAIR provides. And no surprises, it's coupling HPC simulations to these AI models, right? So I could go on to lots of the details, but just appreciate the computing part of it. The basic algorithm is as follows. And by the way, although this is protein design, I assure you something very similar occurs for materials design. Something very similar occurs for fusion reactor design, right? So you start off with what is essentially a generative approach, and in this particular case, not for everything. In this case, it's RF diffusion coming out of David Baker's lab to propose new structures. This is a constraint problem. It's not just any arbitrary random structure, but it's constrained. So the structure has some guaranteed properties. You use something called protein MPNN to optimize the sequence, and then you use AlphaFold to get the structure, and you rinse and repeat until, and that's the pipeline sequence you see there, until there's some convergence between the structure that you want and the structure that you are getting from here, okay? And obviously you know that this is a legit structure. Obviously, and we've done this, and so what you also need to do is you need to kind of constrain this with experimental data, with more simulations, and importantly, you want to improve the AI model, the continuous learning, right? And so the idea, and this is not being done, is you want to be doing this in addition to be doing this. That's why this is the basic algorithm, and these are the refinements, and that's what we're going to be using NAIR for. So this is just to say that we've done the basic part, and now using the runtime systems, we're going to be kind of invoking the various services that are provided by NAIR to try to improve this. So just very quickly, yes, we are able to use the resources more efficiently. Interesting, but maybe at this stage boring. Here's the catch. These are trends. These are very early results. Green is when we use our AI systems coupled with simulations. Red is when you don't, and you at least start seeing the trends, if not rigorous answers. These are the quality of the proteins by various measures. We don't need to get in. These are 3 different metrics, right? And in these 2 cases, higher is better. In this case, lower is better. You start seeing the trends. And obviously, as we do this at scale, we'll be able to. Not only are you doing this at, the trends are that they're better proteins. You're starting to see that you get higher throughput. So all I want to say here is you're not only using HPC and AI to do science at scale better and faster, but you're also using the same capabilities of the AI to improve the science and the HPC to improve the AI because of that continual learning loop. And just want to close out by giving an example close to Ulf's heart of using optimal surrogate builder. So the AI is being improved by virtue of the simulations through a framework, which again, the details are not important. Just want to say you can bring your active learning policy, active learning algorithm, and use this at scale to try to design whatever material you may want to, or in this particular case, for neutron scattering data analysis, come up with smart algorithms using this framework that allows you to either improve your target acquisition, data acquisition, or target function. And just trying to show you that these are all done at scale where you can improve your AI systems so as to eventually lead to less amount of data at the same level of accuracy. Okay, so that's all to say that I hope you appreciate technology trends and application make workflows critical. I hope you appreciate a particular class of workflows, AI-coupled HPC workflows, and for reasons that are both driven by the application as well as the technology. And I hope I've given you a small flavor of some of the research challenges of doing this at scale. Thank you very much.